Thank you. So there are two main observations which motivated the work I'm going to present here. The first is that initial peak displacement correlates well with the world record peak ground velocity. There are several studies done in several regions of the world, and the same observation is done for peak acceleration, peak acceleration, and peak velocity. And the second observation is that, as Simone has shown in the previous presentation, that we need to expand the p-wave time window to correctly estimate the magnitude. And maybe we need to expand this window to correctly estimate the final peak ground motion. So the scope of my work is to ask the question, can we design an offline, can we design an algorithm which can be based on the analysis of the p-wave in a continuous time window, and can we combine the information that we have in real time at the same time from displacement, velocity, and acceleration. So we used, again, two data sets from the Japanese data bank, about 37,000 three-component records from the KeyNet and KickNet data banks. One data set is used for calibrating the empirical relationships, and the other one, the star here in these figures, is used for testing the procedures. Our data span a very rather large magnitude interval, and also expands to a very large distance, up to 500 kilometer distance. So the principle of the measurement is very simple. Once we have got the first P arrival, we measure the peak acceleration, the peak velocity, and the peak displacement. And in order to compute the peak displacement, we high-pass filter the trace in order to remove long period artificial noise and baselines. So these measurements are done continuously along the vertical component, so we use only the vertical component, starting from the P-wave arrival. And we expand the time window. We consider two cases. One, up to limiting the time window to the S-wave arrival, which is known theoretically or manually picked. And the other one, which is more feasible for early warning application, is to use an unlimited pre-wave time window. So we verified and recompute the scaling relationships between peak displacement and peak ground velocity. Here, peak ground velocity is used as a proxy for the instrumental intensity, and we use the well-known table of the USGS shake map for having a reference on the peak ground velocities. So, as you can see from this figure here, one value of peak ground velocity is mapped in two values of peak displacement, which corresponds to the limits given by the 1 sigma errors on the curve. So for our work, we defined the two different thresholds. One is between intensity 4 and intensity 5, corresponding to very light potential damage. And the other one is between intensity 6 and intensity 7, which correspond to moderate potential damage. So for a given threshold value on PGV, you get two limits for PD, depending on the standard error on the regression line. And given an observed value of PD and a measured value of PGV, you have a diagram which defines four regions where you have a successful alarm, successful no alarm, the green portion of this diagram, then false alarm and missed alarm. So you have a sort of decisional scheme which can be used to assess the performance on the data. In order to combine the information coming from different observed quantities, we transformed each quantity in a normalized parameter, which is 0 before of the first limit in peak displacement, then increase linearly and take a constant value of 1/3 in the for PD larger than the average value plus 1 sigma. We did the same for the 3 parameters, and then we built this combination of peak displacement, peak acceleration, and peak velocity, which is simply the sum of the 3 transformed variables. So now we have just a single parameter, which we have to test for establishing if our system is good performing or not. The problem here is that we have to set a threshold on this parameter that we call WS. And for doing this, we use data recorded at distances smaller than 100 kilometers and magnitude greater than 6. And so for this data, we varied the values of the threshold, WS, and build this curve. One gives the number of false alarms versus the threshold, and the other one gives the number of missed alarms as a function of the threshold. And our choice was to select the value of the threshold, which minimized both false and missed alarm. But of course, you can use this calibration to decide in your specific case which weight you can give to false on or missed alarms. So, given the scheme that helps us to assess the performance, we did testing on the Japanese testing database. These are 14 events with magnitude greater than 6, about 800 records. And for these events, we adopted both unlimited and limited pivot time window, and we provide overall statistics, alert times, and lead times. Then I will show you a few examples of a scenario earthquake study, just to see how this methodology works in some specific cases. So here you have 2 columns. The first is for a limited P-wave time window, and the second is for a limited P-wave time window. And the 2 rows represents the performance of the system given the threshold associated to the intensity measurement 5 and intensity measurement 7. You can see that as we expect, the use of an unlimited P-wave time window, which is a window which goes for all the vertical record, increases significantly the number of false alarms, while a better figure we get by using a limited P-wave time window with a moderate number of missed and false alarms. Alert lead times can be studied only retrospectively, because they cannot be obtained in the real time by these procedures. But we wanted to understand how these quantities could depend on magnitude and distance. So, which is the definition here? So, the lead time, the alert time, is the time of the latest PD, PV, or PA overcoming the threshold. So this quantity can be computed only for when we alert the dark green situation. And the lead time now is the difference in time between the arrival of the PGV computed on the horizontal components and the alert time. Here, again, we show the alert time and the lead time for the two intensity thresholds. And we plotted the points as a function of the distance and as a function of the magnitude. You see the colors becomes light as we go to a larger magnitude. You can clearly see that there is a correlation between magnitude and distance, since that only data from large earthquakes are available at distances larger than 100 kilometers. The dotted lines here are theoretically computed alert times and lead times, assuming a P-wave window of 3 seconds and a standard TS minus TP arrival. So we know that alert times is not constant with distance, actually is not constant with magnitude. It's around 2 6 seconds within 100 kilometers, but then increase rapidly as a function of the distance, again as a function of the magnitude. We interpret this as a source effect, which is related to the shape and duration of the moment rate function, in the sense that we need more time for larger event to reach peak ground motion, which overcome the threshold. On the other hand, lead times increase as expected with the distance, and in case of the largest threshold, we see that most of data are above the theoretical computed lead time. That means we have more lead time available on average on our data, but the slope of the data follows very clearly the theoretical line. So let's go to look at some examples. Here is the 2008 MW 7.2 Iwate-Miyagi earthquake. Again, we show on the left a limited period time window, and on the right a limited period time window. And you clearly see that when limit the period time window at a time which is smaller than the S-wave arrival, we get a very good performance of the system with a reasonable count of missed and false alarm. But if we expand the time window, we get a significant large number of false alarms. The case of Tohoku is very peculiar, because when we use a limited period time window, we have a lot of missed alarms, especially along the coastal stations. And this is because the used window is not enough large to catch the maximum ground shaking for this event. When we expand the period time window, we remove almost totally the missed alarms, but with the cost of increasing the false alarms. I wanted to test what will be the case for moderate size events in Italy. We consider the two events of magnitude about 6 occurred in L'Aquila in 2009 and Emilia in 2012. You see that the coverage of the station is not as dense as in Japan. Even in the case of the Emilia, we have a very good station distribution. So in general, what we see that the performance in terms of number of missed and false alarm is good. But the important thing is that the lead time is very small. It's actually of the order of 3 seconds. So this lead time calls for the question what to do in this very short time available for risk mitigation actions. One point to outline is that anyway, we are at the distances which are within the blind zone of the network when we use a regional approach. We have a poster that we have presented today where we show that the size of the blind zone in Italy due to the accelerometric network is around 30 kilometers in radius, or 30 to 40 kilometer radius. So it will be advantageous to use this kind of approach, because we can have a very rapid alert in the blind zone. So I came to the conclusion. So we have developed and tested offline an early warning method which uses the amplitude of P waves, both acceleration, displacement, velocity, and we try to combine the three information to get an alert. So we pointed out the problem of limiting our P wave time window. Of course, if we decide to limit the P wave time window, we have to develop algorithms to automatically detect the S wave arrival, which is not a simple task in real time. The use of unlimited P wave time window increases significantly the number of false alarms, but as we have seen in the case of Japanese event, it drastically reduced the number of missed alarms. So it's a matter of decisions. Alert times are small, within 100, 200 kilometers, but we saw that they increase with distance, and we think that this is related to a source effect. Finally, we applied this method to moderate size events, the ones that we expect in Italy in general, and the conclusion is that we should face with relatively small lead time if we apply this method. So the real question is what to do with these few seconds. Thank you.
Questions?
Perhaps you said it at the beginning and I missed it, but so what's the scenario you see this kind of approach being preferable over using the kind of network-based approaches that, like Presto, for example?
So actually, this is an on-site method, single station based, but as soon as you have stations which have a good communication system, you can think of put together the alerts that any stations could provide. And so you could integrate this kind of approach in a network-based if you really want. But it is originally designed as an on-site method, single station.
この PV の PV の PA このsite application factor is important for estimate correction of the difference of the site application factor. Did you include your result site correction? How do you treat site application factor?
Good question. I think if I go to the first slides. The implicit assumption we are doing here about this problem is that the same amplification is for the P and the final PGV at the same stations. And when you look at the correlations, you don't see. Of course, you have some scatter around the average lines, which could include some site-specific effects. But on average, you see that this side effects is not dominant in the analysis.
Okay, thank you.